Hello, thanks for inviting me to the Geometric Analysis Past, Present, and Future 2022 Spring session. I'm Diptaishik Choudhury. I'm going to be speaking on this work on CMC foliations of quasi-Fuchsian manifolds near the Fuchsian locus and Hamiltonian paths in cotangent space of Teichmuller space, and that appear out of the data of the CMC foliations. This is in collaboration with Filippo Mazzoli and Andrea Seppi. The latter being my advisor. So, what we are going to do in this introductory talk is kind of explain the setting and also discuss the main results. So, we start with a close-oriented surface of genus G greater than equal to 2, and we consider quasi-Fuchsian metric on the surface times the real line. So, the picture would be something of this sort. This is the surface times the real line, a model for a quasi-Fuchsian manifold. How do these manifolds come into existence is that we have this holonomy representation from the fundamental group of the surface into PSL2C, which are the group of orientation preserving isometries of H3, and this image now is a discrete subgroup of PSL2C that acts properly discontinuously and freely on H3 but not on the boundary of H3. So if you see the H3 as this unit as the ball with the boundary at H3 being identified with the complex projective space CP1, then what you have is that a limit set appears on the boundary associated to this action of gamma, which is where the action fails to be free and properly discontinuous, just restricted to the boundary, and it's defined as the limit n going to infinity gamma n dot x, where gamma is an element of the gamma and x is an element in H3, and it can be shown that it falls on CP1. So one characteristic feature of quasi-Fuchsian manifolds are these manifolds that are borne out in this fashion as the with the setup above, this being a discrete subgroup of PSL2C, such that this limit set is a quasi-circle on the boundary of H3. What is a quasi-circle? Well, you could see that there is a quasi-conformal map from the CP1 to CP1, which is deforming a circle to this quasi-circle, and there will be more precise ways of writing it down that will come in the main talk. Or you can just see that we call gamma to be quasi-Fuchsian if the complement of the limit set has two connected components. So I want to say that this boundary of H3 minus this limit set is the union of this dome plus this dome, and it has just two components. And when my limit set is a circle, we call it a Fuchsian group, and we can easily see now that the Fuchsian groups are contained in quasi-Fuchsian groups, and quasi-Fuchsian and Fuchsian manifolds in general are a center of many problems in 2-3 dimensional hyperbolic geometry and have been studied by many experts like Monahan, Thurston, Sullivan, among others. So what we are trying to look at is that surfaces of constant mean curvature inside quasi-Fuchsian manifolds. So what is a mean curvature is that when you have a surface inside a bigger manifold, it would come with the data of the first and second fundamental form. Well, the surface is immersed inside this quasi-Fuchsian manifold. In this case, the first fundamental form gives you the induced metric on the surface, and the second fundamental forms give you the variation of the normal. And what you do is that we get this trace of the 1 inverse 2. This 1 inverse 2 is actually the shape operator, and this half of this is the mean curvature, and you want this to be constant throughout the surface. And actually, I did not say something, but I will mention in the main talk that we have the convex hull, and we want to, or in the quasi-Fuchsian, in the quotient, I have this convex core, which has two pleated surfaces as its boundary, and then I want to foliate the region between the convex core and the boundary at infinity by the CMC H surfaces. So, what is the so moreover, I mean, in this Lorentzian setting, the CMCH surfaces have been well studied, and it's known due to the work of Moncrief that this data of the CMC foliations give you, in the Lorentzian setting, give you a time-dependent Hamiltonian flow in the cotangent bundle of the Teichmuller space. Well, you take the first fundamental from equivalence class and the second fundamental from traceless part, and that somehow identifies with a point in the cotangent space, because points in cotangent space of Teichmuller space are indeed given by these conformal classes of the metric on the surface times a quadratic differential defined on this complex structure, because conformal and complex structures work hand in hand on a surface, and it so happens that this traceless part becomes a real part of this quadratic differential. So what are the main questions that we are addressing are that if quasi-Fuchsian manifolds contain foliation or admit foliation by constant mean curvature surfaces, well, and also the second part is that if you can prove that this foliation exists, you can get a Moncrief type of flow in the cotangent space of Teichmuller space in a similar fashion. So we also note that there is this almost Fuchsian locus, which is a quasi-Fuchsian manifold with a unique minimal surface uh, with principal curvatures, or actually mean curvature. Should be the same because of the fact that a minimal surface for me is the one whose mean curvature is actually equal to 0, with principal curvature ranging in -1 to 1. So the mean curvature is equal to 0, and you want the principal curvatures in -1 to 1, and it so happens that there is a subset of the quasi-Fuchsian space, which is a neighborhood of the Fuchsian locus also, which is called this almost Fuchsian, where you can find these unique minimal surfaces with this condition. And it has been asked by Thurston if these manifolds can be foliated by CMC surfaces, because you know that quasi-Fuchsian manifolds in general are not foliated by CMC surfaces. So what you want to do is that you call the QFS and FS the equivalence class of quasi-Fuchsian and Fuchsian metrics. And the theorem that answers question 1 above partially is that there exists a neighborhood U of the quasi-Fuchsian space inside the quasi-Fuchsian space of the Fuchsian locus, such that every quasi-Fuchsian manifold there is foliated by CMC its surfaces. I mean, a picture would be something like, if this is the quasi-Fuchsian space and this is the Fuchsian locus, then you have a neighborhood which is contained in this almost Fuchsian locus as well, and this neighborhood we are claiming is containing CMC foliations. Every quasi-Fuchsian manifold in this neighborhood contains CMC foliation with uh, values of the mean curvature ranging in -1 and 1. Further, you do the same treatment as you take the conformal class and the traceless part of that. And what you do now is that this traceless part and the conformal class is are so conformal class are orbits of a time-dependent Hamiltonian flow defined in an open neighborhood of the zero section in t star t times -1 and 1. I just wrote IH and 2H because, I mean, just for simplicity in the introduction talk, but essentially we're going to take the conformal class of IH and the traceless part of 2H and show that it's a Hamiltonian flow, where the function is given by Hamiltonian function is given by the area of the CMCH surface multiplied up to a multiplicative constant, which is equal to -1/2 in this case. So these are going to be the setting of these two talks that will follow, and hope you follow the talks and get something out of them, and let me know if you have some questions from there. So thank you.